Good evening and welcome back. Let's see where we were here. So we kind of went through some of these failure theories. We did it kind of quickly. If you have some bearing as to, some idea of what you're doing, it doesn't take much. All you're going to do is, when in doubt, look them up in the back of the book there in the mechanical engineering section. Fortunately, they all have those bits of guidelines to tell you when failure will occur. They can help guide you along, so you don't really have to memorize anything unusual about them. One thing I will point out is that some of these failure criteria are based on yielding, and some other failure criteria are based on ultimate strength. Interestingly, the ones that are based on ultimate strength are said to be used for brittle materials. If a material is brittle enough, then its ultimate strength is approximately its yield strength anyway. They just don't yield much before they break. That's the hallmark of brittle things. So just pay attention when you're using the various failure theories, whether they would like you to compare to the yield or the ultimate. It's a common detail that you could overlook. The last one of these we're going to look at, I think it's the last one in the set here, is distortion energy theorem. And one way that this is presented is based on the three principal stresses. So this is kind of why we've had to delve into this idea of 1 and 2 and 3 and A and B. If you have three principal stresses, well, you always do. If you have three of them and they're non-zero, then you'd need to use that version of the equation. Of course, if one of these is zero, you can pick whichever one you want to put in whichever place. This equation is entirely symmetrical in all respects, so the equation itself doesn't care which value you use as number 1 or 2 or 3, though in theory we're supposed to ordinate them from greatest to least. So if you've got three principal stresses, there you go, there's your version of that equation. Can you tell, looking at this a little bit, there's a divided by 2 going on. That's a little curious in this case, and we're comparing that to the yield tensile strength. So kind of looks like maybe we're actually comparing it to shear, but anyway, we don't need to worry too much about the derivation of distortion energy. Suffice it to say, this is the Pythagorean theorem. It's a three-dimensional version of the Pythagorean theorem. So we're going to square these values, square these values, square these values, add them all up and take a square root, which means it doesn't really matter if something has a positive value or a negative value, except that you're comparing them here, so you do have to be a little careful with that. So this is one case in which we use a Pythagorean theorem, but we can't totally ignore the sign on everything. As usual, tension is positive, compression is negative, and as long as you're using that sign convention, this will work out fine. If you only have two principal stresses, instead of caring about 1 and 2 and 3, we can just call them A and B. So for two principal stresses, this equation simplifies to the second equation. And even better still, if you don't want to bother calculating the principal stresses, but you'd rather just use your input stresses, sigma x, sigma y, and tau xy, well, you're free to do that as well. So we have these three versions of the distortion energy theorem. As well as having three versions, we also have a few different names for this. This is often called the von Mises stress or the effective stress. So when you see sigma prime, that's effective stress. You might also see some people write it as sigma Vm for von Mises stress, all the same stuff. Or distortion energy stress, all the same thing by several different names. So that's listed right alongside the others as a potential failure theory to use for ductile materials in the back, mechanical engineering section of the handbook. Let's give you a chance to try one of these. We've got a strength listed, we've got a factor of safety, and so what's our allowable shear stress for this one? Once you get used to this terminology and you get to, starting out, you'll read a question like that and you'll kind of, be trying to fit things into place. With a little bit more experience with these, after doing a few more, you get to where you can just kind of read the problem and answer it. So some of these get really fast after you've gotten some practice, though obviously initially you kind of have to think about what's going on quite a bit. All right, so we've got 1 vote for answer C. Do we have a bunch more for answer C or anything else? A couple of A's. So because we're asking for the allowable shear stress, a material with a shear strength of 25 would have an allowable shear stress of 12.5. So if we do the Mohr, that's a terrible circle, but if we do the Mohr circle and we find that we had uniaxial stress of 25, that would indicate we're failing with a max shear stress of 12.5. So we've got to give a factor of safety of 5 underneath that 12.5, which means we're going to use a fifth of it at 2.5 KSI, and the answer is A. All right, so we've kind of talked about the idea of given some loading, we can find the principal stresses in tau max, and that feeds into our failure theories. Now we're going to kind of go back and figure out, well, how do we get from actual loading scenarios on actual parts and manage to travel from there to some idea of what sigma x, sigma y, and tau actually are. So enter the discussion here of pressure vessels. We're going to have to take a look at what they've got in the handbook. There are a few different equations used for pressure vessels. And what we see on this slide is just the thin-walled version, but let's take a look in the handbook. Yep, I passed it. Cylindrical pressure vessels. Now, a pressure vessel is a three-dimensional object, right? So it could have pressure in any of 3 directions. And the way we're going to define those directions, if we look at sort of a chunk of pressure vessel here, terrible drawing already, but if I look at a section of the wall of a pressure vessel, it might be stretched longitudinally or axially. So we could have a sigma in the axial direction. It might be stretched in a transverse direction that's tangent to the circular side wall of the pipe. And we're going to call that sigma T for tangential. Or we might call that sigma H as hoop stress, whichever one you want. The book is going to use a T for hoop stress because it's tangent to the curved wall of the pipe. Well, the only other direction left then is sort of coming straight out of the wall of the pipe or going sort of down into the pipe. And that's going to be the radial direction, so we'll have a sigma radial. So radial, tangential, and axial are the 3 different directions that we care about. And as we look at their equations on page 131, we have an equation for tangential stress and an equation for the radial stress. It turns out that the radial stress is simply the pressure. They both have units of PSI or pascals either way. So whatever your amount of pressure is, that is the radial stress on the part. So for internal pressures only, the stresses on the inside wall are those. And for external pressures, the stresses on the outside wall include these. Notice that in both cases, that radial stress is compressive. If you have pressure on the outside, it's compressing the outside. So we see a negative sign in both of those. And the tangential stress, if you've got pressure on the inside, that's going to be a tensile stress. And if you have pressure on the outside, then you're going to have a compressive stress. Now, if you look at the rest of these equations, like the sigma T equation, for example, that's really kind of the same equation, isn't it? In fact, what we might have to make room for at some point, you might run across a pressure vessel that has pressure on both sides of it. Well, truth be told, all pressure vessels have pressure on both sides of them. So you might have atmospheric pressure on the outside and some kind of pressure on the inside. It's really the difference in pressure that we're using for the letter P in each of these cases. And you can see that this equation is exactly the same as that equation. It's just that the pressure is on the outside. It's compressing it. You really could condense these down to one that's just pressure on the inside minus pressure on the outside times all the R squared stuff. It's a minus sign. So really, these 2 equations could be written as just one equation. It's the difference between the inside and outside pressure that creates these stresses. So that's the tangential and the radial. stands to reason we need an equation for the axial still, and of course we find one here. There is a note above this that says, for vessels with end caps, the axial stress is. Okay, well, that is true, but it's also true that for any kind of pressure-containing object, regardless of whether it's a pipe or a cylinder or something with end caps or with no end caps, if there's a pressure, then this is the axial stress. So any kind of thing that to any degree contains some working fluid under pressure is going to have that axial stress. End caps are not required in the least bit. For example, if you had a 500-mile long pipe, just due to frictional, you might have a pump on one end, and you might have an opening 500 miles down the road on this end, but due to the friction with the surface here, well, you might have atmospheric pressure here, you can end up with a huge pressure there. At any point along this pipe, you're going to have pressure. And if you know the pressure at a given location, then you can calculate the axial stress at that location. So end caps are not required. There's no special requirement here. This is the axial stress in any vessel containing a vessel, pipe, whatever, that has a pressure inside that's greater than the pressure outside. Similarly, we could put in a PI minus PO for that one as well. So their presentation of this equation is a little bit limiting. It sounds like you can only use it in a very specific case. You can use it in a lot of cases. We might be able to simplify these tasks by in cases in which the pressure vessels are thin. For thin-walled pressure vessels, we'll change that tangential equation to something much more friendly. And we'll change this axial equation to something that's also pretty friendly. Where is sigma radial? We don't have a third equation here for sigma radial, do we? On the previous page, we said that sigma radial equaled the pressure. Well, it turns out that's still true. For the thin wall pressure vessels, we don't simplify that anymore. It's just the pressure. In any of these pressure vessels, it said, for example, if the pressure is on the inside, then this is the radial stress on the inside of it. It turns out that pressure gets sort of distributed out across the rest of it, and you'd end up with zero radial stress out here at the edge. So the radial stress actually undergoes a gradient from its high value matching the pressure here to zero out at the surface. Or you could say it averages out across the surface. So no difference in calculating radial stress for the thin-walled versions, but obviously the other two equations got less complicated. How do we know when something's thin? If we're going to say we use these for thin-walled cylinders, what's our criteria by which we might call it a thin-walled cylinder? That's captured in this sentence right up here. When the thickness of the wall of the cylinder, whether it's a pipe, pressure vessel, it could even be a rectangle. The distribution of stress is not as equal in a rectangle. For thin-walled, roughly circular pressure vessels, if the wall thickness is about 1/10 or less than the inside radius, then it's thin-walled. I suppose someone could get really picky with this definition. I could see someone trying to make a problem in which the outside radius would not meet this criteria, but the inside radius would meet this criteria. If you ran up against that sort of problem, you'd say, well, it's barely meeting the criteria for a thin wall pressure vessel. The one to use, the correct measure to use here, is inside radius, and they're specific about that here in the instructions. So use inside radius, don't use the mean radius, don't use the outer radius for this calculation. On one of the questions, the wall thickness, use this equation on the question. Yeah. So you saw a question on the exam, you're saying, that used those two little guys right there? Not too surprising. Good to know that that's in use. That's definitely, this whole hoop stress cylindrical pressure vessel thing is a really common section on the NCS exam. Some of the trends we can notice here, notice that the axial stress is literally half as big as the hoop stress or tangential stress. If you go to the scene of a fire, perhaps, where some pressure vessels have exploded, some gas tanks or that sort of thing, when these things explode, they typically explode with a gash down the center that's been sort of peeled back in this direction. So failure under tangential stress due to overpressurization in a fire, for example, is not uncommon. It makes sense. The tangential stress is twice as big as the axial stress. You don't tend to see these things where like the top of them has blown off of the bottom half. That would be an axial failure. You don't tend to see that. We're interested in this axial stress because at any given point in this material, we've got the combination of axial stress and tangential stress and radial stress. And so those act in concert with each other. You can't just consider one without considering the other. And we might also have particularly fabricated pressure vessels where we have a weld or something going across this direction. And we might be interested in whether or not that weld would fail under axial stress. So we do find a use for each one of these in turn, but so even though the axial stress is half as big, it still becomes an issue in a few cases. Well, there, hopefully now you'll remember that the axial stress is the one that's half as big. And so we've got all their different equations there. The next way to put stress on something that we'll discuss is to put it under torsion. If we look at each tiny little element, if we look at a microscopic element of this, we might see that that little element is getting twisted to some degree. And of course, that angle of twist is gamma, where gamma is the that interesting shear strain thing we looked at before that might have units, might not have units. Technically, it's radians per unit length, but we can approximate it as inch per inch kind of thing. So we've got our angle that each little bit of this is deformed, and that's consistent all the way down the length of it. If we looked over at this end, we'd find that this end has not rotated at all, whereas the far end has rotated some amount delta, and at each given distance along the length, that theta value would be different. You know, over here that theta value is 0, and over here that theta value is not 0, and that would be proportionate all the way down the length of the thing. This diagram calls it theta. The equation in the book calls it phi. And that angle of twist, whether you call it theta or phi, is TL over JG, which is not that different at all from delta, which was PL over EA. The load was P, now the load is torque. The length appears in both of these. On the bottom, we have a description of the cross-sectional area, as opposed to J, a description of the cross-sectional area and how it twists, and E, the modulus, versus G, the modulus. So we'll use the elastic modulus in one, and we'll use the shear modulus in the other. Those are very similar equations, TL over JG versus PL over EA, pretty related to each other. So if you find one, you might feel confident in using it for the other. It becomes apparent from that we're using J in this equation as a substitute for our understanding of how the cross-sectional area performs, as opposed to material properties, loading, and dimensions, which we see in the other factors. So our cross-sectional shape is described as A in one case and J in the other. J is the polar moment of inertia. During our dynamics class, we said that, we took a look at mass moment of inertia, because that applies in the dynamics class. And then from there, we stepped back and found that oddly in the statics section of the book, they discuss area moment of inertia, even though we never use it there. We only use area moment of inertia here in mechanics of materials. We haven't run into it yet, but we will. In addition to the area moment of inertia I, we could, for example, look at this round cross-section and say that if we were to bend this bar about an x-axis, that would involve an IX through the centroid. If we were to bend it about a y-axis, that would involve an IY through the centroid. And it turns out J is the sum of those two. Kind of surprising, perhaps. So if we take a look back at the statics section of the handbook where they listed the equations for area moment of inertia, let's see if we can find some values of J and confirm that J is the IXC plus the IYC. And here we go. So the IXC and the IYC in this case would be pi a to the 4th over 4. And if we add two of those together, we get pi a to the 4th over 2. And yep, that is how we calculate J. Yes, G is the modulus of rigidity, also known as the shear modulus. Thanks. We've also got a J calculation done for us here for the sort of annular cross-sectional shape. We don't see J values for some of the others, but would you be able to add these two values together and figure out how hard it is to twist a semicircular cross-section? Absolutely. So just keep in mind that you can use the IXC and the IYC in each of these cases to get you a J. A couple of them they've provided for you, but most of them they have not provided J for you. This is on page 99, the end of the static section, though we're using it in Mechanics of Materials instead. And if we go back to page 98, we see the kind of triangular and rectangular cross sections. And the only one of these for which they already provide you a J value is the rectangle. Well, it's the easy one. But as we mentioned, if you need to twist something with a non-right triangle cross section, then you add that IXC equation to the IYC equation and you'll get it. So TL over JG, J is describing how hard it is to twist the thing. T is the load, L is the dimension, the length, and G is the material property, the shear modulus. So let's give that a try. Tell me what you get for this problem. So we've only got one answer to this one. Kind of hard to compare based on that. Who else has an answer? All right, 169, good. So that's answer D with quite a bit of accuracy. No problem with accuracy on this one then. Anyone else getting a different answer? So we've got our TL over JG equation, and we're told that we're going to have 4.5 degrees of twist. And that angle has to be entered into the equation in radians. So there's your first little wrinkle. Very similar to everything else we've done. Anytime we see an angle in an equation other than a trig function, it has to be done in radians. So good, there's no surprise there. So we can enter that. We're looking for the torque. The length is 0.5 meters. The J is, I'm sorry, that's the G. The G is 28 billion PA, and 38 billionths of a meter to the 4th is our J value. So yeah, 169 Newton meters. Answer D. What's the page number? No idea. Well, a better thing, rather than ask what the page number is, let's ask what word are you going to search for to find it. So if you found the page, or if you haven't found the page, what do you think would be the key word for this? Since we've got the total angle of twist, the term twist isn't used very often, you could try the word twist. That's probably going to get you there. You could search for torsional strain or torsional shear or any. The point is, every time you look something like this up, be looking on that page for key words. Don't try to remember page numbers. That doesn't work as well. Also, they might change the handbook between now and whenever you take the exam. If you get delayed by 3 months, there's a good chance they bring out a new handbook and some of the page numbers change. So focus on keywords once you find the stuff. Obviously, you got to find it first, so that's part of the challenge. All right, so that's pressure vessels and torsion. We've already done tension and compression. That was just P over A. The next thing we can look at is bending. We have a couple of sign conventions here, and we're going to end up doing shear and bending moment diagrams. And hopefully, with a little bit of practice, you can get to the point where shear and bending moment diagrams are no big deal. in order to do them consistently and sort of do them the same way everyone else does, we're going to use some sign conventions here. Positive bending makes the beam smile at you. Negative bending makes the beam frown at you. Now, if you were in outer space floating around and somebody else were turned completely on their head, then your idea of positive bending would look like negative bending to them. So again, these are just sign conventions. They don't determine how the world works. They just help us keep track of them in a consistent way with each other. The same is true for shear. Positive shear would be holding something in your left hand and pushing down on it with your right hand. That would place the object in positive shear. If someone's standing right in front of you watching them do this, then to them it would look like negative shear. So it's all about point of view and frame of reference. The point is, this is a sign convention or set of conventions that we can use so that our diagrams look similar. There's some rules here for shear and bending moment diagrams. We're going to skip right past them and actually sort of learn these experientially and play around with them and see if we can end up developing those rules on our own. We're going to need to do shear and bending moment diagrams because we want to come up with two values. V is the magnitude of shear, and M is the magnitude of a moment. And our diagrams will help us keep track of the value of V at every point in the beam from its left to its right, and our moment diagram will do the same for the moments. We can then identify places where, for example, if we think there's a strong bending moment right there, then maybe we thoroughly analyze that particular location on the beam to try and figure out if it's in danger of failure. So we're trying to figure out where the maximum stresses are, and we're going to start by figuring out where the maximum shear and bending moment might be in a given shape. So looking at this diagram, our first task really is to find the reaction forces. As we learned in statics, to find the reaction forces, we might ask two questions to keep us headed down the right path. Is this problem symmetrical? In this case, the loading is symmetrical, but the supports are not symmetrical. So we'll say, no, it's not symmetrical. And then we can ask, which reaction force is greater, the left one or the right one? Looks like the right-hand reaction force would be the greater of the two. So let's make sure that our answers coincide with that. We don't have any multiple choice answers to compare with, so we do need to go ahead and do this sort of the accurate way. And we might do this by way of sum of moments about, oh, it looks like they've done sum of moments about the left-hand side here, I think. Being 16 meters long, this 100 Newton per meter distributed load can be represented as a 1600 Newton load that is 8 meters from the left-hand edge of the beam. So we've got 1600 times 8. It's spinning us clockwise, so that's been called negative. Then reaction force on the right is 12 meters away, and it's going to try and force us the other way. So we've got positive reaction force on the right times 12 meters. And that allows us to calculate the right-hand reaction force of 1,077 newtons. Subtracting that from 1,600 gives us the reaction force on the left of 533. So now we have some values to use. This is 533. This is 1067, both in newtons. Now we can start working on a shear diagram for this. Our shear diagram is a graph with the horizontal axis of the graph being locations along the beam. Typically we call this sort of an x-axis, and typically we start that over on the left. And you can see this symbol here indicating start your measurements from the left, and x will increase as you go to the right, which is the traditional sort of direction to use for this. If this were a real structure, if this were something someone actually built, what do you think that left-hand support might be? Give me a few options of, if you needed to support this beam, how would you support it? We might balance it on a steel post, right? Well, I mean, we've got the locations. So there's a support on the left end. There's a support kind of in the middle. Maybe those supports are I-beams. Maybe they're 4x4 wooden posts. How we calculate some of them. You all have an amazing knack for asking questions before their time when we haven't had a chance to get there yet. We'll get there, I promise. We could, let's see, we could swing a rope around this, right? Maybe there's a rope hanging off of this thing that's holding it up. That could apply that load. Is there any way we could apply a load to that that would actually apply a point load? What is a point load anywhere? Maybe in what we've got over here at the end, maybe we've got a 4x4 post with a nail sticking out of it. Maybe we balance this whole thing on the head of that nail. Is that a point load? Well, I mean, sort of, but I mean, even at the microscopic level, the head of that nail is going to have a little flat spot on the end of it from that beam. So every load, no matter how we support it, every load we apply gets distributed against some amount of, or get distributed across some amount of cross-sectional area. Or since we're doing 2D diagrams looking left to right, some amount of left to right width is present in every support. So if this is a 2x4, then we're supporting it across 1.5 inches. If it's a 4x4, we're supporting it across 3.5 inches. If it's a 6-inch I-beam, we're supporting it across 6 inches. And if it's the head of a nail, we're supporting it across maybe a 50th of an inch. But when we use this construct of a point load, well, that's a theoretical thing that doesn't actually exist. There's no such thing as a point load. Everything's a distributed load. Let's say, just for the sake of argument, that maybe this distributed load on the left is actually an 8-inch wide concrete masonry unit stack, for example. Just something 8 inches wide. If that's the case, let's take a look at this left-hand end of the beam. Imagine that before we set this thing up, I had actually painted this beam. Maybe I painted it blue. Is there any force on the end of that beam that's trying to sort of scrape the paint off the end of the beam? Like that far left-hand edge, is there anything shearing that off or anything trying to scrape up the side of that beam? No. So when I start my shear diagram, I can pretty safely start my shear diagram on the left-hand side at 0 if I think that's what that support represents. And then somehow over the first 8 inches, I would be applying a total of 533 newtons across 8 inches. And by the time I got to the 8-inch mark, by the time I got here, the shear in that beam would be a total of 533 newtons pushing up and sort of 1,600 newtons pushing down, the distributed load pushing down. So if I cut this at the 8-inch mark, I would see 533 newtons worth of shear at that 8-inch mark. And it turns out that as I go across my support, that shear stress varies linearly, and so my shear diagram would start at 0 and rise up to 533 over the width of that support. If that support were twice as wide or 4 times as wide, then this slope would change. I would be distributing that across a wider area than I am. Or if we go with the approximation given in our original problem statement here, if we pretend that it actually is just a point load, that is, it's supported across a negligible width, then I can say that I really and truly do have 0 shear at the end, and I really and truly also have 533 shear at the end. I've collapsed that support down into an infinite slope, so I do have a value of 0, I do have a value of 533, and I do have every value in between applied at that left-hand edge. It's going to be a little important in a particular kind of situation that comes up pretty often. I'm not going to say, well, the shear stress at the end of the beam isn't 0, it's 533. That wouldn't be true. I also can't say, well, the shear stress at the end of that beam is 0, it's not 533. That's not true either. It is 0, and it's 533, and that's all kind of part of what's involved in this infinitely narrow point load kind of thing. We have values from 0 to 533 all in the same location. It's a bit odd, but that's what we've got. From there, we're going to start pushing down on this at a rate of 100 newtons per meter. So by the time we get to the 1 meter mark, what's going to be the height of my shear graph or shear diagram? So we start at a value of 0, we instantly rise to 533, and then by the time we're 1 meter across this, we'll have lost 100 newtons per meter. So this value, the value of the distributed load, is the slope of our shear diagram. How about at 2 meters? Where do you think we'll be? Well, we're going to lose another 100 newtons per meter, so we'll be down at 333. Where will this graph hit 0? Do we all agree on that figure, 5.33? Yep, and Catherine has even given us an equation by which we can find it. Yeah, so by the time we get to 5.3 meters, something interesting is happening. So we'll say that's right about here. At 5.33 meters, we've gone up to 533, we've lost 100 newtons every meter, and we've made it back down to 0. So that's what our graph is looking like. Does the slope of our graph change at that point, or does the slope of our graph remain the same? Well, we've got the same distributed load, so we're going to have the same slope, and we're going to continue down with that same trend all the way until the 12-meter mark. What's going to happen at the 12-meter mark? We've got a point load there of 1,067, which is a distributed load totaling 1,067 newtons that's distributed over exactly 0 area. So we just have an infinite slope. And we're not really sure I have this scaled right, so it's kind of hard for me to figure out where exactly to put the end of this line at first glance. Can you tell me what this value is going to be right here? So I can add the 1,067 and end up in the right spot. Can you tell me what that value is? Catherine's equation ought to help you out. We have a magnitude of negative 667 on our shear diagram at that point. If we add 1,067 to that, that's going to take us up to positive 400. And then from there, our same trend will continue, and it should make sense that over here on this right-hand end of the beam, nobody is trying to scrape the paint off or shear off the right-hand side of that beam. So yeah, we should end up at 0, and we do. In fact, if we'd noticed that we should end up at 0 over here, then maybe what we could have done is said, if we're going to reach 0 after traveling for 4 meters at a slope of 100 newton per meter, then we could work from the right-hand side back to this 400 point. And then we could drop down 1,067 from there to our negative 667, which would probably have been an easier way to calculate that 667 value. You can work these problems from left to right. If you want more practice, then work it from left to right, and then start over and work it from right to left and see if you get the same values. You should in every case, and you should be able to do that in every case. So there's our shear diagram. What key points do we find here? Like what points look to be interesting? Well, at a distance of 0, 12, and 16, we have interesting things going on. We also have something interesting at 5.3 meters. So those are all points of interest on our shear diagram. How do we get the negative 667? Well, 0 plus 100 newtons per meter times 4 meters gets us to 400. And then 400 minus 1067 gets us to negative 667. That's how you get to it. That's how you get that value from right to left. If you want to start on the left and get that value, then you do 533 minus a slope of 100 newtons per meter times 12 meters, and that gets you negative 667 from the left. I think the right-hand version might be easier, but really they're both pretty reasonable. So there's our shear diagram. Now, if somebody asked you to calculate the stress caused by shear, you might not be interested in what's happening at the 3-meter mark or the 5-meter mark, but you know that the worst shear stress anywhere is this magnitude. So that 667 seems to be sort of a key point, and we might take that shear value, and in a moment we're going to, well, in a few minutes, we're going to learn how to turn that value of V into a value of tau. But at least we know now where on the beam to look, where we think a failure might occur due to shear. Now let's do the same for moments and figure out what we're going to do there. The moment diagram is made in exactly the same way the shear diagram is. But instead of basing our moment, so with the shear diagram, we base the shear diagram on the free body diagram. We're going to base the moment diagram on the shear diagram. So the values, so any value for an area of distributed load on this diagram gave us a slope for our shear diagram. Let's do the same here. Let's take a magnitude here for this area. This magnitude is at 533. That's the initial slope of our moment diagram. It's kind of sufficient for us to say, well, the slope is positive, and we can scale it in the way we want. So let's just use a positive upward trend there to start our diagram. It certainly seems like nobody's trying to twist the end of this beam off. So I'm pretty safe to start at a moment value of 0. Similarly, I don't think anyone's twisting the end of that beam, the right-hand side, off. So I think we're going to end up at a moment value of 0 as well. So again, you could start from the left or start from the right. Either one would work. If we had an applied moment, for example, if this beam were cantilevered off of an anchor on the left, then we might have an applied moment at the side, and that would start us off with some non-zero value on our moment diagram. In this case, though, we're going to start our moment diagram at 0, and we see a slope of 533 newtons. I'm guessing that 533 newtons doesn't sound like a slope to most people. What would the slope of our moment diagram be? So our moment diagram is we're plotting moment versus x. X is going to be in meters. The units on moment are going to be Newton meters. So the slope of this would be rise over run, Newton meters per meter, which is newtons. So if we look at this 533 newtons and say, well, that's 533 Newton meters of moment for every meter x across the beam, that sort of makes sense. So we start at 533. It's kind of pointing as though it, at the 1 meter mark, we'd have a value of 533. That's what that slope means. That slope is not going to remain constant like this constant horizontal line did there. It's going to trend downward, and by the time we reach 5.3 meters, its value is going to be 0. So I can come over here to the 5.3 meter mark, and I know my slope there is going to be 0, so that's horizontal. So we start with an upward trend, and that upward trend decreases in slope gradually and eventually reaches a slope of 0 at the top. That shape is going to be parabolic. So if you wanted to draw it accurately for whatever reason, it's a parabola. It's not sort of a circle, it's parabolic. What's the magnitude of our moment going to be at the 5.3 meter mark? When we looked at this distributed load, for example, if we started on the right and wanted to work back to the 4 meter mark, the amount of change we saw in our shear diagram was equal to this area here. This area is 4 meters wide, 100 newtons per meter tall. So what we did is, to get this value here, we integrate from the right-hand side back to that point. So integrating the distributed load diagram is how we get our values on the shear diagram. It didn't feel like we were integrating when we did it, but we are. So let's do the same. Let's take the total area under our shear diagram and use that to find the magnitude of our moment. So what is the area of that triangle? It's going to be 1/2 base times height. Our base width is 5.3 meters. Our height is 533 meters. That's going to take us up to a value of 1422. If you keep all significant figures and a ridiculous number of them, I think it was 1422. And that's Newton meters. So now we have that first 5.3 meters fully defined. We know it's a parabola, we know it starts upward and then it trends toward horizontal. It starts at 0, it ends at 1422. If somebody really wanted to torture us, they could ask us to find the moment at some point between 0 meters and 5.3 meters. I haven't seen anyone do that. But, solving a parabola for a particular value is something that we should be able to do. Just, I've never seen anyone do it. So we think the 5.3 meter value is important and the 0 meter values are important. What other values might be important? Well, let's look at what's going to happen as we continue across this beam. We've got the same trend. Now we're going to be subtracting area underneath our curve in the same way that we were adding area underneath our curve before. In fact, by the time we get to a particular location, all this area that we added to get up to 1422, we're going to have subtracted 1422 and we're going to hit 0. Where do you think that's going to happen? At what distance along the beam? At what location do you think we will have lost all that 1422 that we gained? At 10.67 meters. Yep. So we should be starting with a slope of 0, and our slope would trend downward to a slope of negative 533 newtons, or newton meters per meter. So that shape, though I haven't done a great job of drawing it as such, that shape should be parabolic and symmetrical between 0 and 10.7 meters. Our increasingly downward slope trend should continue to the 12 meter mark. And we could try to total up this area here, perhaps, and say, well, that's a width of 6.67 meters wide and a height of 666.7 newtons. So we could find the area of that triangle if we wanted to. But it's probably a little easier just to kind of switch gears and start from the right-hand edge of that beam. How do we know where it crosses 0? Well, due to the symmetry of the shear diagram about this 0 point here, we think that the area of this triangle is equal to the area of another triangle here that is the same width. So we're adding another 5.33 meters to get to 10.67. So we see some symmetry in the diagram about that 5.3 meter part. We could try to sort of take the area of this triangle and subtract the area of this triangle and figure out what depth of our moment diagram we get to at that point. Well, where is the shear 0 has been asked. So Jennifer is asking, where is the shear 0? Well, that raises a good question. Let's look at our shear diagram. At what locations on the shear diagram does it reach 0? It reaches 0 at 5.3 meters. Anywhere else? At 12? Anywhere else? At 16? Anywhere else? At 0. Yes. So that's the importance of that idea that we really and truly have a 0 shear at that point, and at this point, and there, and there. If you pass through 0, then you've got 0. So we find 4 interesting points, and at each of those points, as Jennifer's pointed out, we might have a maximum or a minimum, and sure enough, we find our maximum value looks like it's going to be at 1422, at least that's a local maximum. And then down at the 12 meter mark, we're also going to pass 0, so that's another local maximum. That turns out to be a local minimum. And if we're interested in that value, we said we could sort of take the little triangle and subtract the big triangle from it. It's a little easier, I think, to start over here on the right-hand side at 0 and find the area of this triangle. What's the area of that triangle? That's 1/2 4 meters times 400 newtons, which looks like an area of 800 Newton meters. So as I progress from the 12 meter mark to the 16 meter mark, I'm going to be picking up 800 Newton meters, which means I probably start at negative 800 Newton meters and come up to 0. Should this be a straight line? Or should it be sort of circular? Or should it be parabolic? It should be parabolic because we see a sloped line here on the shear diagram, and that indicates a changing slope. And should it be sort of concave downward or concave upward? I'm not sure if that's the best way to say that, but so it should be concave upward, you think? Well, let's test that. What should the magnitude be at the right-hand edge of the beam? Just kidding. Wow, wise choice there. Well, the magnitude of our moment diagram should be 0, and the slope of the moment diagram is the magnitude of the shear diagram. So what's the magnitude of shear at the right-hand side? At the right-hand edge, the magnitude of our shear diagram is 0, so we need to have a slope of 0 here. So we're going to hit this right-hand side at a slope of 0. 4 meters back from there, we have a positive slope. We're gaining 400 Newton meters per meter. So we got a slightly positive slope there, a horizontal slope there. We're going to trend parabolically down toward horizontal over that last 4 meters. Okay, but does that answer your question of the moment diagram curve because of the distributed load, or is it always curved? Okay, so there is no always anything. So not every moment diagram is the same shape. We're responding to what we see in the shear diagram to make that moment diagram. Now, our transition from the free body diagram to the shear diagram follows exactly the same rules as our transition from the shear diagram to the moment diagram. So if we had a shear diagram that looked like this, then we'd have a moment diagram that had triangles in it. So where you see constant 0 slope on one diagram, your next diagram will have a consistent slope on it. So if you have a constant value here, you have a constant value for slope in the next diagram. If we see angled lines in this diagram, then the next diagram is going to be parabolic. So for example, the graph of this distributed load would be the y value equals 100 Newton per meter. The slope of the graph of, so that's the graph of this horizontal line here that defines that distributed load. The graph of this line would be y equals minus, well, this is minus 100 newtons per meter x plus some y-intercept plus 533. There's the graph of that line. This equation is the derivative, it's the integral of this equation. And then the graph of this one would be y equals negative 100 newtons per meter x squared, which is what makes it a parabola, plus 533x plus some other constant value, which I don't really care about. But the point is, this is the graph of a horizontal line, this is the graph of a sloped line, and this is the graph of a parabola. As we take these integrals, we go from line to angled line to parabolic to cubic to quadra, whatever. We keep increasing as we go from one diagram to the next. So our final result is a shear diagram that has a few key points, 533, 0, 667, 400, and 0, and a moment diagram that has a few key points. At 5.3 meters, it reaches a maximum of 1422. At 10.67 meters, it reaches 0. At 12 meters, it's at negative 800, and it's at 0 at each of its ends. So what we're going to be able to do with this is, looking at these two diagrams, what locations across the beam from left to right do you think are in danger of failure? I think that bending moment is going to cause the most bending stress at the 5.3 meter mark. So I might analyze what's going on at this beam at 5.3 meters. At the 5.3 meter mark, I have 0 shear and a moment of 1422. So that's going to be kind of easy to analyze that point. At the 12 meter mark, I have a shear value of negative 667, which is going to cause some kind of shear stress. And I have a moment value of negative 800, which is going to cause some kind of normal stress, sigma. So I'll have a combination of sigmas and taus at 12 meter that might be concerning. So how do we turn we're going to look at how to turn those V's and M's into taus and sigmas, but let's kind of do a couple more shear and bending moment diagrams along the way. Here's one for you. Find the vertical shear at the midpoint of the beam shown. Is this problem symmetrical? Yes. So are we pretty clear that the reaction forces are both of a magnitude P, whatever that is? All right, so we can take our original diagram, kind of turn it into a free body diagram by scribbling all over it, as we often do. What's our shear diagram going to look like? Well, it's going to include a value of 0 and every value from there down to negative P. Is there any change in that diagram going to happen over this next little length? I've got a distributed load of 0, which means I've got a slope of 0 all the way across distance L, and then I'm going to have an infinite slope taking me up back to 0. I've got a distributed load of 0 giving me a slope of 0 on the shear diagram here, and then I'm going to go up a distance P to a value of positive P, and then a distributed load of 0 means a slope of 0 here, and then we'll come down some distance P. So there's the shear diagram, and the answer to the question is the vertical shear at the midpoint of a symmetrical beam is always 0. So when I told you to look at your problems and ask, is it symmetrical? Well, this is another piece of information that symmetrical helps you with. If it's symmetrical, the shear in the middle of it is 0. And your shear diagram, if it's symmetrical, is going to be sort of mirrored across the center, both in the X and the Y planes. So symmetry helps us kind of recognize what we're going to get. How about the moment diagram? Is anyone trying to twist the left-hand side or the right-hand side of this beam off? If not, I'll start and end at 0. And what should the initial slope of my moment diagram be? Well, at least I got one answer. Not P times L, it's going to be P newtons, well, negative P newtons, which means P Newton meters per meter. So I'm going to lose P Newton meters for every meter of length across the beam. So wherever 1 meter is and whatever P is, that's what I'm going to lose. I'm going to lose P Newton meters for every meter. So I have a downward slope of P, and is that slope going to be changing over the first length, L? No, we're going to keep that same slope all the way across from 0 to L. And then what's going to happen to my moment diagram? I've got a shear value of 0, which means a slope of 0 all the way across the middle of this thing. And then I need to add this area. I'm going to have a slope of positive P for a distance L. So what is the magnitude of this sort of low altitude there across my moment diagram? What magnitude will my moment diagram reach at its lowest? Well, we started at 0 on the left and we lost an area of P times L, so this is P times L. All right, so we have a slope of negative P, then a slope of 0, then a slope of positive P, and that's going to take us from 0 down to negative PL and back up to 0. So our moment diagram for a symmetrical beam is symmetrical. Whereas our shear diagram, oddly, is kind of like mirrored across the center in both X and Y, which is odd. So here are just the examples for that. Now we've got 3 or 4 more examples. If you want, you can work these just as they are, where we haven't been given any numerical values, we've just got letters. Or if you're more comfortable doing it, instead of saying load P, you can just say, okay, I'm going to say that P is 100 newtons. And if there's a dimension A, I can pick a value of and say, well, that's 7 meters, and B is 3 meters, and L is 10 meters. If you want, just assign numerical values to these things if that helps you. I find that helpful. That's what I typically do. I don't like messing with P times L and a slope of P and that sort of thing. So I'm just going to pick some values here. We'll say that's 100 newtons, and this length is 10 meters, and that's Yeah, 7 meters and 3 meters, maybe something like that. So we'll see if using those values we get the same results they do here. This beam is not symmetrical. I think reaction force B is greater than reaction force A, and if we do a sum of moments about B, we'll have 100 newtons times 3 divided by 10, which would be 100 times 3 divided by 10, which is P times B divided by L. So that's good, and that's 30. Then we're going to drop down 100 newtons, which should take us to minus 70, which they've described as PA over L. We can start from the right-hand side and find reaction force B. So reaction force A, we said, was 30. Reaction force B is going to be 70, and sure enough, we should go from negative 70 back to 0 at this end of the beam so that those numbers all work out. So we go up 30, down 100 in the middle, and then up 70 at the end. That seems pretty reasonable. What is the total of this area under our shear diagram? We add up all that area, we're integrating that portion of the diagram to get our moment value. Our moment diagram is going to start with a slope of PB over L, whatever that means, a slope of 30 newtons, 30 newton meters per meter. And it's going to keep that slope all the way across to the 7 meter mark. So we know we're going to have a straight line there. Notice again, this horizontal line here gives us a straight angled line there, as it always will. And what is that total area? Well, this is a height of 30 and a width of 7 meters. So that should take us up to 210 Newton meters. How about this area over here on the right? Well, that's a width of 3 and a depth of negative 70. That's going to lose 210 Newton meters, and that makes sense as well. So we'll lose all 210 and end up back at 0. So a point load on a free body diagram becomes an infinite slope on the shear diagram. And like the endpoints here, the infinite slope in this case is a place where we cross 0. So that's an inflection point on our moment diagram. Anywhere it crosses 0 is a maximum or minimum. And a distributed load on our initial diagram will give us an angled shear diagram. A similarly horizontal line on a uniform distributed load on our free body diagram would give us an angled line on our shear diagram. Similarly, a uniform height on our shear diagram gives us an angled line on our moment diagram. If we look at the next example, we'll see another example with a distributed load. This is a lot like the first example we worked. That uniform horizontal distributed load, so it has one magnitude all the way across, that's going to result in a uniform slope. So a horizontal line here ends up in an angled line there, and then that angled line here results in something parabolic there. So, and we know due to symmetry that we'll have a point of interest where the shear diagram crosses 0 in the middle. So we'll have a local minimum at 0 and L, and we'll have a local maximum at L divided by 2. And the area of this triangle is the magnitude QL squared over 8 that they've used for the top of that diagram. So that one's very similar to what we already worked. The next example they gave us here is not all that interesting. It's a series of point loads. Every point load is a discontinuity or infinite slope region on our shear diagram. And in between those discontinuities, we have a uniform slope here because there's no distributed load, so we have no slope. This slope of RA gives us a slope here, and then a little less of a slope there, a negative slope here, and an even lesser slope there. Where the shear diagram crosses 0, we do have a local maximum on our moment diagram as predicted. The last one is kind of interesting. What do you think? Let's see here. Tell me what you think about this one. Can you agree we have no shear, no moment on the left-hand edge? So both of our diagrams are going to start at 0. Similarly, we seem to have no shear and no moment at the right-hand edge, so both of our diagrams are going to end at 0. We're going to start our shear diagram with no point load at the end, but a negative distributed load. So that's going to shear downward at a slope of 1,000 pounds per foot, rather. They gave us a dimension here of 4 feet, so what number should we have at the 4-foot mark on our shear diagram? -4. So we'll drop down to an altitude of -4 on our shear diagram. That's -4,000 pounds. And then we'll have a discontinuity RB. And ostensibly, as shown here, that's going to point us upward. Now, we haven't calculated that reaction force yet. Maybe we should go and do that. In fact, I'm pretty sure we should. So tell me what your value is for reaction force B. What is the magnitude of reaction force B? I'm going to do a little sum of moments about C that will allow me to solve for reaction force B as something divided by 16 feet. For that distributed load on the left-hand side there, what magnitude and distance am I going to use for the moment caused by that distributed load? It's 4 feet wide and 1,000 pounds per foot tall, so it's going to be a total of 4,000 pounds. And what distance from B is the centroid of that little distributed load on the left? I'm sorry. I said I was going to do moments about B. I actually wanted to do moments about C. I forgot that they labeled A as the sign. I'm sorry. I'm trying to do moments about C. I got the letters mixed up. So that was the correct answer to the question that I asked. I was just asking the question I didn't want to ask. So the distance there is 18 feet. And that's trying to spin us clockwise. So we're going to call that positive. Anything else go in this equation? We have reaction B at 16 feet. We've got that accounted for. We have a moment, an applied moment of 12,000 pound-feet. So we just throw that applied moment in there. And is that positive or negative? Well, if we use positive clockwise for the first one, we better use positive counterclockwise for Q's moment. We ought to use positive counterclockwise for this one. So 4,000 times 18 plus 12,000, all of that divided by 16 is going to give us a value of 5,250 for the reaction force at B, which is going to take us directly up to a magnitude of 1.25. And then we'll carry right on across. What do you suppose reaction force C is? Well, if this is 4,000 pounds and this is 5,250, then reaction force C must be a downward 1,250. So reaction force C brings us back down to 0 as predicted, 1.25 thousand pounds. So there's our shear diagram. If you looked at that shear diagram, would you have noticed that there was a moment applied to this beam somewhere, like an applied moment of 12,000 pound-feet? You might not have noticed. You don't really see it explicitly listed there. Obviously, it affects our reaction force magnitudes, but it's kind of hard to see it. It's hard to visualize that applied moment just by looking at the shear diagram. All right, well, what's our moment diagram going to look like? It's going to start with a slope of 0, because I know my shear diagram starts with a value of 0. So we'll start with a slope of 0, and our slope is going to get increasingly negative over the first 4 feet. At the 4-foot mark, I think we're going to have a local minimum, and what will the local minimum value be on the moment diagram at the 4-foot mark? So I'm going to start with a slope of 0. I'm going to end up with a steeply negative slope, and so my moment diagram is a parabolic downward, concave downward thing. This area right here is 4 feet wide and negative 4,000 pounds tall. So 1/2 4 feet times 4 feet should take us down to -8 again, shouldn't it? So we'll reach a magnitude of negative 8,000 foot-pounds. Everybody okay with that value? That's the area of the triangle on our shear diagram. And then we're going to add to that the area of our shear diagram. But I think something interesting is going to happen here, kind of right in the middle of that little span there. So let's work from left to right to kind of see where we end up at the, I guess, the 12-foot mark. Can't read what I'm writing on any of them? Ooh. Okay. I will try and write them a little better. You're using a phone. So you're using a small screen, ostensibly, right? Okay. So what will the magnitude of our moment be at the 12-foot mark? The print's small for all of them, so we got a weird kind of zoom thing going. Can you read the numbers that are typed on the page? So is it just the stuff that I'm writing by hand that's weird, or is it like impossible to read anything? Oh, okay. So it's probably more that it's messy than it's small, unless they're scaled differently. My numbers are larger than their numbers are, but mine are apparently less clear, which would not be terribly surprising. You don't see any. Oh, all right. Let's see if we can fix Nick's display issue by doing that. Nick, you've been looking at a blank screen for all this time? That's not good. Okay, so what value will our moment diagram have when we reach the 12-foot mark? Well, if we start on the left at 0, we're going to drop down by the 4-foot mark to -8. And then by the time we reach the 12-foot mark, we're going to add up the area of this little rectangle here. What's the area of that rectangle that takes us from the 4-foot mark to the 12-foot mark? It's 8 feet wide and 1.25 newtons tall. So that's going to be 10. And so we're going to reach at the 12-foot mark. We're going to reach a value of -8 plus 10, which will bring us to a value of 2. And how are we going to get there? Are we going to get there using an angled line or something parabolic, or parabolic up, parabolic down? An angled line. Yeah. So our shear diagram suggests a slope on the moment diagram of 1.25 Newton meters per meter. So we start at 8, and then we add 1.25 meters, and we add another 1.25 Newton meters. On the next meter, we add another 1.25 Newton meters, and we keep on doing that until we get to 2 at the 12-foot mark. All right, let's start at the right-hand end, and I'm pretty sure we've got nobody twisting the right-hand end off, so let's start our moment diagram at 0 there. And on our way to the right-hand end at 0, we'll be adding this area in blue. What's that value? Well, that's another 10 Newton meters. So to get from the 12-foot mark to the end of the beam, we're going to add another 10 to get to 0, which means we must be down here at -10. So what is it that happens exactly at the 12-foot mark? A discontinuity that takes us from 2 to -10 due to that applied moment. So that applied moment is effectively kind of a point discontinuity kind of thing on our moment diagram. And it takes us from 2 down to -10 because it has a value of 12. Now, that might seem a little counterintuitive, right? That for it to take us down on our moment diagram when the moment's magnitude is positive? I agree. These sign conventions are not all compatible with each other. So it takes a little fiddling to justify mathematically why that applied counterclockwise moment results in a drop in the moment diagram. But if we back away from all the engineering stuff and we look at this beam just sort of from a layman's point of view, would it make sense to you that if what if I tried to just draw the deflected shape of this beam, right? So we know it's going to be touching a support here, and it's going to be touching a support there. If I were to draw how this beam deflects under these various loads, what do you think it would look like? I think the left-hand side would be kind of tilting downward like that due to that distributed load. And I think I think the rest of it's going to be bowed. It's going to be kind of bowed upward a little bit, but I think at the 12-foot mark, I'm going to see a twist in the beam that's kind of going to take us from, it's going to make the left-hand side look a little positive and the right-hand side look a little negative in bending. So you think we've got a little bit of a twist like that in the center of the beam, where just to the left of it, we've got positive bending, and just to the right of it, we've got negative bending. And then that negative bending trend is going to kind of continue to the end, and this brief positive trend is going to continue down that way. So we've got negative bending on the left, negative bending for most of it, until somewhere in here it transitions to positive bending, and then negative bending all the way to the end. And that's true of our diagram. We've got negative bending everywhere except this brief little area to the left of the 12-foot mark. So it works out. It makes sense. So the interesting thing about the applied moment, that is sort of the most unusual or most difficult thing they might possibly throw at you in a shear and bending moment diagram thing. The interesting thing about the applied moment is you don't readily see it in the shear diagram, but you do see it as a discontinuity in the moment diagram. A change moment over an infinitely small width. Suddenly applied moment. So that's shear and bending moment diagrams. If you want, you can look back at this list we saw briefly here, and you should find that everything we've done is consistent with that list. No, I wouldn't suggest that you need to memorize any diagrams. I think that's a futile thing to do in general. I mean, you could, but memorizing diagrams is not really what intelligent engineering sort of minds would want to do. We want to understand how they're created rather than just try to memorize them, right? And while we've delved into this process and we've spent quite a bit of time doing each one of these, realistically at exam pace, it should take you like, I don't know, maybe a minute and a half, 2 minutes or so to do shear and bending moment diagrams for any of these. Also, one of the things we often can tailor our work to the question. If the question says, where is the largest bending moment in this and what's its magnitude, then you don't really have to calculate this value or that value. You just need this value. So don't do the whole diagram, go just find exactly what you need. So we kind of get this here subtracted from 0, and you're down to -10. So even when asked about them, you often don't need the entire shear and bending moment diagram. You just need to find the key points and key values. All right, now we know how to find a value of V we're interested in at some location and a value of M we're interested in at some location. And now it's time to figure out how much stress does a bending moment cause, and the answer to that is here. The stress due to bending at any location in the beam, for example, if we say we've got M equals -10,000 foot-pounds there, given that M value, what kind of stresses is that going to put on the beam? Well, because that's a negative stress, we know that that's going to be causing a sort of negative bending tendency at that location, which is going to put the bottom of the beam in compression and the top of the beam in tension. We also know that the center line, or the centroid, axis of the beam is going to have a bending stress of 0. So do you all agree with those assessments? We're going to have tension at the top, compression at the bottom, and 0 along the center line of a beam that has a negative bending moment. If the moment value is -10 for a beam of a given cross-sectional shape, we can find the I value, and as we travel from the neutral axis up some distance y, we're going to end up with a tensile stress or a positive value. So let's say we travel up a distance y for, I don't know, 0.03 meters. Well, then we're going to 0.03 meters there. And so we'll have, what I'm trying to do here is justify the presence of this negative sign. If the moment is negative and the y value is positive, that's going to give us tension, which is a positive bending stress, so we have to put a negative in this equation. If the bending moment were positive, if we instead sort of curved our beam like this, then we'd have tension on the bottom of it and compression on the top of it. So as we travel up a distance y, so if this were positive moment and a positive value of y, we end up with a compressive stress. So that's why there's a negative sign in that equation. That equation, negative my over I, allows you to use I as a description of how hard it is to bend this cross-section, and m, which we found from our moment diagram, to calculate the bending stress at every location from bottom to top across this beam. Where is the maximum value that this equation is going to reach? Well, it turns out to be at the point furthest from the center line of the beam. If we describe the points furthest from the center line as having a distance c from the center line, then we can say that the maximum bending stress occurs at the extents of the beam. This one's symmetrical about the center line, so we can go up a distance c or down a distance c, and we can say the magnitude of the max stress is mc over I. So when y equals c, we'll find our maximum. Do you notice that there's no negative sign in here? And that's kind of a problem. That equation allows you to calculate the maximum magnitude, but because they forgot to put the negative sign in there, it's kind of lying to you about whether it's tension or compression. So when you see that equation, mc over I, that is the maximum magnitude of the stress, but they forgot the negative sign when they wrote that equation in the handbook. That should have a negative sign in front of it for the same reason that this one should have a negative sign in front of it, because c is measured positive upward, just like y is measured positive upward from the center. And in positive bending, the further you go up, the more negative your stress becomes. So they messed up in the handbook. If we want to refer to these using different terms, instead of using the area moment of inertia, we can use something called the section modulus, which is I divided by half the height, in this case, or the most extreme point from the centroidal axis. So it's I divided by c gives us a section modulus, which means we can do m over s, and they forgot the negative sign there as well. That is, this only gives you a magnitude, and it's your job to figure out whether it's positive or negative, because their equation forgets to comment on that. So m over s, yeah, that's the magnitude you should be using. But if you really care about its direction, then you need to kind of watch which direction it's in. The next thing we run into is, so that gives us the ability to turn an m into a sigma. If you're just interested in finding the sigma at the maximum point, then m over s or mc over I. The maximum normal stress on page 136 is sigma x equals plus or minus mc over I. For a symmetrical cross-section, that's fine to say it's plus or minus mc over I. Excellent. So have they changed that now? It now says plus or minus on this? Oh, that would be great. That's at least I mean, it's kind of good. Really, it's just minus. But at least they change it to say plus or minus. But yeah, it really should just be a negative sign. For the same reason, it's really just a negative sign there. But okay, they got closer. They acknowledged the possibility of the correct answer. If you had a beam that instead of being symmetrical, like maybe it's triangular, in which case the centroid would be a third of the way from top to bottom, then your maximum stress, if this is, let's say we put this in positive bending, your maximum stress would be a tension down here at this point, and C would no longer be half, C would be 2/3 of the height of this thing. And so then it would be sort of important to figure out if there's a negative sign or not, and there always would be. All right, so we can turn M values into sigma values. We can also turn V values into taus, and that looks a little more strange somehow. We know what I is. B, according to the diagram, is just the width in the direction we're not shearing it. So we got a B value there, and that seems to be the width. They've used Q in their description here, where Q is A prime multiplied by Y prime. A prime is this little area up here, and Y prime is kind of pointing to the middle of it. Let's look at their descriptions and their instructions on this, and leaves a little bit to be desired. They could have just written this equation as minus VQ, I'm sorry, that defeats the purpose of what I was about to write, minus V A prime Y prime over B. Not sure why they chose to use Q. Do you want to? Yeah, we'll give you a break in just a second. So we know B is the width, and I forgot the I. We know I is the area moment of inertia. We know V is the value of interest from our shear diagram at some particular location. We're going to have to figure out what A prime and Y prime are. So yeah, let's go ahead and take a break. And we'll do it for 10 minutes, which will take us to 55 minutes after the hour. So yeah, thanks. We'll see you then.